Hey, chemistry, how you doing? Time for another flipped lecture. We are going to start a series of chapters that deal with properties of matter in various states. And so we're going to look at gases first as the least dense of them, and then we'll look at the other states of matter later. So here we are jumping into properties of gases, and it's a gas, so we'll have a great time. Yeah, here we go. I know, that was hilarious. Okay, most of the times, properties of a gas can be explained by the kinetic molecular model. So the kinetic model of matter, that all matter is made up of little pieces of something that are moving. That's also the fundamental assumption of physics. So the view of matter that everything is made up of little particles in motion is everywhere, and that is the underlying assumption of nature, right? Diffusion can be explained by this because gases will spread out uniformly to fill their container. We observe that, and the reason that we observe that is because these particles are all moving and their motion is random, and so they're going to bump into each other, they're going to bump into the walls of the container, and eventually they will have spread themselves out to uniformly fill a space. That is diffusion. Another property of a gas is fluidity. You can pour a gas. It's kind of like a liquid in that sense. Now, if the gas is less dense than the atmosphere around it, then it's going to pour up, which, you know, kind of strange. But you can see examples of gases that are being poured down as well, and we'll look at that in some demonstrations in class and a lab. So fluidity, gas particles may behave like a fluid. They can be poured in some cases as long as the densities are right. Gases can also be compressed, and so there is a lot of space between gas molecules, and so you can push on that fluid, that gaseous body, and compress them. Liquids cannot be compressed, or at least not meaningfully. Solids also cannot be meaningfully compressed, and so gases are the only state of matter that can be compressed. Gases also exert pressure on their containers. They are colliding with each other and with the walls of their container, and those collisions impart impulse forces to the outside of the vessel, and all of those collisions on average are about the same amount of kinetic energy being imparted to the wall of the container, and so a body of gas maintains a relatively constant pressure on its container as long as things like temperature and volume aren't changing. Directly related to temperature and inversely related to volume. So the more temperature, the more kinetic energy because of heat that you add to the gas particles, the faster they're going to travel, the greater kinetic energy they're going to impart on their container when they bounce into the walls, so the higher the pressure. Inversely related to volume, as volume goes down, you're squeezing on a gas, the volume goes down, the pressure goes up. If you expand a gas, the pressure goes down. And all of this makes kind of logical sense. We did cover this already in physical science, so this should be a review for you. Okay, moving on. So we're reviewing gas laws, and again, you had this last year, or actually 2 years ago in physical science. Charles' law expresses the relationship between volume and temperature. They are directly related. As you increase the temperature, if the pressure stays the same, then the gas gets bigger. As you compress a gas, if the pressure stays the same, the temperature goes up. So volume and temperature are directly related to each other. As the temperature rises, volume also rises, and you can see that mathematically here. V1 over T1 equals V2 over T2. Volume in the first instance divided by temperature in the first instance is equal to the same 2 after you've made some change. So if V goes up, then this is a larger V than this is, then this T must be a larger T than this is, so that they maintain relationship. Okay, so they're still equivalent fractions. Okay, let's look at an example of that. If I take a balloon and I fill it with 0.75 liters of gas at a temperature of 25 degrees Celsius, and then I rapidly cool it by like pouring liquid nitrogen over it, okay, down to 0 degrees, what's the new volume? I'm going to leave the pressure the same. So volume initially, oh, we need to go into kelvins. That's right. Sorry about that. We need to go into kelvins first. We don't want to be in degrees Celsius for any of this math. Okay, so here we go. 0.75 liters of air and 298 K. And then at 0 degrees Celsius, it's 273 K, and I'm looking for this missing V term. So Cross multiply and divide, and that's the easiest way to do that. So 0.75 times 273 gives me this number, and then I'm going to divide that by the 298K, and I'm going to get this number. So 0.68078 liters, but that's not the correct number of significant digits. I need to be able to express this in the right number of significant digits. So 2 digits, right? 0.07 liters, about 9%. So it lost 25 Kelvin in thermal energy and shrank about 10% in volume. Boyle's law, also review. Boyle's law relates pressure and volume. So here we're talking about making a gas larger and smaller and looking what the pressure does, assuming the temperature doesn't change, okay? So P1 V1 equals P2 V2. These are inversely related. As one goes up, the other goes down. So if the pressure 1 is less than pressure 2, if this is a bigger number than this is, then in order for the multiplication to be the same across both sides, this V must be a smaller number so that they're still multiplied together to be in equivalence to the first one, right? So throw in some quick numbers. If 2 times 6 is equal to 3 times what, right? 3 times 4. They both equal 12. So if this got bigger, this had to get smaller. Okay, they're inversely related. That's Boyle's law. Wow, excuse me, Boyle's law. Here's an example of that. A diver with a total lung volume of 1.35 liters, that's a full breath of air, takes a deep breath, filling his lungs completely, and then swims up, stupid diver, from a depth of 40 meters, 5 total atmospheres, to the surface without exhaling. What happens to him? The short answer is he's dead. But let me show you why. So P1 V1 P2 V2, that's my equation. That's Boyle's law. 5 atmospheres of depth. 1.35 liters of air in his lungs. He then swims up to 1 atmosphere on the surface, right? And what's the new volume of that body of air? Well, it's pretty simple. I'm going to multiply across the known side, 5 times 1.35. And then I'm going to divide by 1 to get the unknown volume. And we find out that the new volume of that amount of air is 6.75 liters. His lungs had a full breath of 1.35. Now it's got 6.75. What happens to him? Well, he popped. The air in his lungs went from a volume of 1.35 to 6.75 liters. While it's highly unlikely that anyone would resist exhaling during ascent, not blowing out enough air is the single most common diving accident. My dad had one of these injuries, but thankfully he didn't pop. So here's pictures of people being treated for air embolisms. As a diver, you always say ho, ho, ho on your way up the water column so you blow out all that air as it's expanding, right? Gay-Lussac's law. Temperature and pressure, this is another one that we've reviewed already. So pressure and temperature are directly related. As pressure goes up, temperature goes up. As pressure goes down, temperature goes down. And so again, it's a division problem, and it's to maintain equilibrium. As if this P gets smaller, this T got smaller, so that the two fractions are equivalent to each other. P1 over T1 equals P2 over T2. And then the combined light gas law puts all of these together, pressure and volume and temperature. So Boyle was straight across PV, Charles was PT, and Gay-Lussac's is VT. And so as we combine them into one mathematical expression, we have P1 over V1 divided by T1 equals P2 V2 divided by T2. And all of the terms here will be equivalent to all the terms here. So we can watch any of these things change and be able to predict what will happen at the end. Okay. And then there's Dalton's law of partial pressures. This one we're not going to do a whole lot with in chemistry, but just know that as we add up the pressure of various gases in a volume, the sum of all of the pressures imparted by just that one gas, all of the other gases in the container, will add up to the total pressure in that container. So in this room, the air pressure is 1 atmosphere. About 85% of what I'm breathing right now is nitrogen, so nitrogen represents about 85% of the pressure in the room. Does that make sense? Oxygen being about 10%, so oxygen represents about 10% of the pressure in the room, and the other gases make up the rest. So You add up the pressure of all the component gases, you get the pressure of the entire thing. Alrighty. Just a quick illustration of that. If the pressure of hydrogen gas is 2.9 atmospheres in a container, and the pressure of helium gas is 7.2 atmospheres in that container, if I put those two gases together, that same volume, both those gases together will have a pressure of 10.1 atmospheres, the 2.9 plus the 7.2. Okay, so it's a pretty simple idea. If you have any questions about this, please let me know. You can put them in the comments field below. I'll do my best to answer them quickly. Otherwise, I'll see you tomorrow, and we'll keep trudging through these lessons. Jesus loves you, and so do I. Have a great day.